this.
One sec,
title.
Darius.
Yeah.
I'll do an introduction. Okay. Welcome back, everyone, to another HyperSDK Developer Community Call. The team has been hard at work coding a lot, so we're happy to give you some updates. This call will give a quick update on the EVM HyperSDK compatibility, and then we will finally get to talk about the Vryx PoC and benchmarks. We'll start with Darius talking about HyperSDK EVM compatibility.
Yeah. Hello, everybody. I'm going to share this screen here. I've been working a little bit in the past weeks to see what execution model for the EVM would look like on top of HyperSDK. So I've started this discussion thread. Let's see, the URL is discussion 815 on the repo, and any and all feedback is welcome. The core idea is that we really don't change the get code, and we try to interface with it where the EVM is trying to write its state to its persistent area. We just kind of put an interface there and get all the keys that are changed and like map that to HyperSDK keys. One of the key issues that hoping to get some feedback on is the difference between the EVM and the HyperSDK, where the EVM, you don't need to specify upfront which keys you're going to access. And in the HyperSDK and some other like blockchain programming models, you do need to specify which keys you will access. So definitely what we've been doing so far is like having the person that's, or the entity that's constructing the transaction, like a wallet, run the transaction against current state and make a list of like all the keys that are accessed and kind of hope that it would re-execute the same time at execution. But of course, that's not guaranteed to happen. Like some other state could modify the program and cause it to run differently. So that's one area we're hoping to get a bunch of feedback on. In terms of like execution and fees, there's some details that are also looking for feedback. So one area is authentication, where like how will we handle EVM style signatures or that type of thing. Nonces are another area for feedback. Pretty much we hope to disable them as much as possible and use the HyperSDK replay mechanism, HyperSDK replay protection. And with gas, we're setting the gas price to 0, so we'll charge the HyperVM fees, and probably will modify the storage opcodes to be cheaper because their fees are being paid in the storage dimension. And we'll use gas as a proxy for like the compute units. Yeah, I've also coded up a test that it does some like creates some tokens and then trades them via Uniswap. Of course, some of the transactions end up failing, but it's pretty stable. So definitely, I would consider that a short summary of what I've been working on. So any questions or feedback, either here or on the discussion, feel free to reach out.
Is there any chance you have that demo up and going? Any availability? I don't know if you have that nearby on your computer. If not, like just a trading thing, so people can see kind of like the EVM interactions on it. If not, like I think if you can scroll back up, I think like one of the big question marks that we've been discussing back and forth is how much of a cut to make in the EVM versus just to try to use it out of the box. I think we've internally like maintaining the fork of Go Ethereum or a number of forks of Go Ethereum is quite a time-intensive and delicate operation. And so there's been a lot of appetite to see if with this project we could more or less minimize the diff we actually make into into Geth or like any other EVM execution environment. The issue is that you need to come up with some sort of mapping, like Dariush has mentioned, between like some of these core concepts and like the HyperSDK, where there may not be like a need to have those other than just trying to maintain the minimal cut, versus saying like, hey, like we don't want any of these things. Let's go mod the code and like remove any notion of them, and try to make the interaction or like mechanism that's actually being integrated more minimal, but at the same time have it diverge potentially widely from like any sort of upstream EVM execution. So I think that's been one thing, at least I've been going back and forth on. I'm not sure, Dariush, if you have any thoughts there.
Yeah, so our modifications to, I built this on top of Subnet EVM, of course, because like Avalanche ecosystem and like keeping an eye on like what we could do for our own ecosystem. But our changes to upstream are very minimal for this. Pretty much it just allows for the passing of precompiles to the like core VM package and only uses that. So it's pretty much that. In terms of the demo, I'm seeing if it's going to run. Yeah, I think it's going to run. I can share. Let me try to stop it.
The demos I love you have to just when you pull out a commit, that thank God you have like commits, right? So you can go exactly back to the place and time when things are working.
Yeah, I think you just need to like check out this branch. It's called EVM call experiment, and then like be in this directory, and then you just run the load tests. So this will take a little bit to download some like testing frameworks, and then yeah, it'll like do this.
So I think the thing you should mention there is like when it's running this, like what is it actually doing, right? Like there's like a relayer kind of that's calling out to get these keys and.
Yeah, so this is creating the tokens and like contracts, deploying them, and then doing several rounds of trading. So let's see if I have. That's way too back. Yeah, so this is like showing that, you know, it's done 12 rounds of swapping 1,000 transactions, 1,000 of which succeeded. And this is like showing the total balances for the tokens that are left. This is like accounting for some slippage. This is like pretty raw developer stuff, but you can see that as we go down the round, some of the transactions do not succeed, so successes go down.
Yeah, on that success failure case, I think this is something that we've also been going back and forth a lot about lately. I know, Steven, we've had some conversations about this too, around like the state key mechanism. So this is obviously representative of a conversation broader than just the one we've been having, but also in the space, like what the right approach is. So like we've spent a considerable amount of time optimizing the state key path. So we're about to merge a PR. Is William on here? Give him a quick shout out real quick. Yeah, William has been working on extending the executor to allow you to basically optimize execution based on whether or not a key is a read or a write key. So like it will execute read keys concurrently, even though they're conflicting, which is pretty cool. Like I'm not aware of anyone else that actually has finished implementing that. It has been a multi-month process to get closer, but one thing that people talk about, and this is a perfect demo to example that, is, you know, you have to do all this key tracing. Now, if you optimize your virtual machine or like your implementation with that in mind, and like have data structures you use that try to minimize like the keys that are moving around, because you don't require like the value to also be included, you just require the key to be included, so it's okay if like the value changes. There's obviously another group of people that say, hey, maybe if like most state is stored in memory anyways, like there is no benefit to prefetching from disk. Does it make sense to just optimistically try to parallelize these things using something like or like state transitional memory, state transactional memory, or something like that. So, Stephen, I know you've had some thoughts here. I don't know if you want to share anything.
Yeah, I mean, basically, it's just it can be a big like architectural decision on like whether or not you want to like expect all state to be in memory versus like supporting all state being in memory. So like currently with the existing state key approach, right? Like you can specify your caches to be arbitrarily high, and so like HyperSDK is kind of like tunable on like, if you want beefier machines, then you have like, bigger caches, and then you can like have more your, state in memory, and it's going to run faster, things like that. Versus like, if you say, you know what, if we say everyone's going to just keep the full state in memory, we don't necessarily need to have this, slider of things that you can choose from. And then you can say, okay, we might actually not necessarily need these state keys. So I think the big question at the end of the day is like, what is like the UX of issuing transactions on the VM, right? So like, I think if you have a VM that's like designed for a HyperSDK, I don't necessarily think the state keys are too bad, but I'm very interested on the actual like numbers that we get out of the EVM kind of drop in, because obviously the EVM isn't designed to like avoid for like state conflicts, and like especially the contracts built on top of the EVM aren't designed for that. And so if we can get like good enough results with the state keys, then that's one thing. But if that ends up being an issue, so that's kind of the problem space. There's also some like other technical reasons on like why you may or may not want to keep state in memory. So I don't know if we want to dive into the Vryx stuff. That I
We
won't.
can maybe
I
dive
won't
into
talk
that
about.
after the.
Yeah, I won't steal
sure.
Patrick's thunder or anything. So but there are other technical reasons on if you may or may not want to keep stuff in memory. Definitely,
Yeah, I mean, I think
that's a very big decision because architecturally it can impact a lot from the UX side.
I mean, I think with the EVM stuff, part of the appeal, right, is for most, is just that you can drop in your EVM contract and it just runs. So if we're breaking that assumption because like we want folks to optimize like their Solidity for this like sort of state key execution model, I think it already begs like questions of like what we're actually pursuing here. Because are we pursuing then, trying to be EVM bytecode compatible you can drop in? Or are we more just saying, hey, like you want to write on Solidity, here's your Solidity, like you need to think about exactly what you're going to do and how you're going to touch it, but it's more of a developer environment rather than something that's trying to just have drop-in optimal support. Yeah. I think Solana also like reckoned with this a bit when they were playing around with like some of their transpilers where like people could just like take, some code from some language and then just like transpile it. And then you'd kind of look at it, or at least what I've been told is like, you'd look at it and be like, yeah, I don't know if that's the right, like, it's not going to be optimal because they also have a state key mechanism. So I think the point you brought up, which was interesting, is like usually the issue with the optimistic concurrency control is that you end up potentially having to replay a transaction execution in the case that things fail. But if you are trying to operate at such a high throughput, like if any single transaction execution takes more than like barely any time, like you're not going to hit that throughput anyways. So if the assumption is that like the execution time is already very short, one additional like retry or even like 20% retry rate should be totally tolerable by the system. So unless you have like an absolutely worst case workload, which, if we're talking about that, then, it's a lot less appealing maybe. But that's kind of the frame or lens I've been thinking through.
Does anybody have any questions for Darius or Patrick about the EVM implementation currently?
Very much a proof of concept to flesh out the design, to be clear. I think we're still figuring out what the right approach is to try and get it to some sort of production place, but based on the appetite from developers, it seems interesting that we pursue it at some point.
Sweet. If there's no questions, I think this is a nice segue into Vryx.
Yeah. So over the last all right. So yeah, first off, keep this stuff maybe to ourselves until the video gets posted in a few days, hopefully. This is all public, so you can go find it. But yeah. So I'm going to share some links in the Telegram group just so it's easier to keep track of rather than here. Well, actually, no, you're here. I'm going to share with you here. So I've been doing for the last few months work on the Vryx proof of concept. So if you check that out, you'll see that this is quite a large diff, I guess, in terms of like what I've been doing. I mean, in a nutshell, like the Vryx stuff has forced us to rethink like a lot of the design directions of some components, which is fine. Like, you know, the HyperSDK got to a point where like it was stable or like in a direction, but there were a number of known inefficiencies. And with the Vryx stuff, a number of those things are changing. Funny enough, the interface for like the developers actually building their own virtual machines on top of the HyperSDK changes minimally, if any. So to me, that was a good litmus test to say like the interface that's exposed is you know, not terrible at least. But everything underneath that interface has changed dramatically, you could say. And so the point of all the proof of concept is really to just assess the viability of Vryx and like see if there were any unknowns that kind of came up that would have derailed or could derail a potential like production implementation of Vryx, which, spoiler alert, there were none I could think of. So there were like a few tweaks. You know, I decided that we needed to make to the Vryx specification, which I haven't published yet. But the core ideas worked well. In fact, they worked, in my opinion, really well. So on this branch, there's basically one file which you can look at, which all this other stuff is great. But the part that you care about is how can I get the throughput you're talking about? So we created a reproducible DevNet deployer, which basically just assumes you have an AWS account. And if you have an AWS account, you can just run this script and it will automatically spin up a cluster of 50 validators, 5 API nodes, and then one dedicated load test machine, one dedicated monitoring machine, and basically automate an entire load test that will continue indefinitely until you turn it off. That also allows you to view metrics of that. So I recorded myself doing this demo end to end, and I'll post that shortly. But the video for that you can watch on your own time is here. Again, keep this to yourselves. So that's a full end-to-end demo of deploying my own DevNet and then having that DevNet go from 0 to 100,000 TPS. Now, when you talk about throughput, there's a lot of characteristics that matter. So like how many accounts are there? How many accounts are active? Like how many regions are there? And so in this particular case, there are 10 million accounts, 2.5 million of which are active every 60 seconds, 95,000 of which are active every second. And there are 5 regions, so spread equidistant roughly around the world. So inside of, I believe it's Oregon, Ohio, India, Japan, and then Europe. So it's not like a contrived, like single data center, like 10 accounts, like how fast we can go. This is like supposed to represent like a real production workload. And like I said, I think we did it. So I'll share the images now from the load test. And so all the data that I'm about to share with you, you can reproduce by running my script. So first off, here's the transactions chart. So to prove also that things were stable, I decided to run this over 5 billion transactions, so just over or just underneath a day. And so this is if you look at so all this monitoring infrastructure is spun up for you from scratch. So like you're like, how did I generate these pretty graphs? Like you get that when you just run the script. So it's all automated for you. And when I mean one command or like simple script, I mean one command. Like you just run one command and everything happens behind the scenes. You don't have to have any infrastructure experience whatsoever. As long as you have an AWS account, it will work. And so initially what the test does is it funds a set of accounts. So like all 10 million accounts, which it does here. And then it will slowly scale up. Basically, this is all configurable, but 1,000 transactions it's 5,000 transactions per, I don't know. There's some ratio of which it speeds up and then gets to your target and then just tries to keep it at that target. So in this case, it got up to the 100,000 TPS target and then just sits there until I shut it off, which was at this point. So some of the spikes you'll see here are just because in this particular test, I like under provision the disk IOPS a bit. So if you run it now with the script, it will be flat. But that's the rationale for that. And so then like, it's kind of crazy at this throughput, how quickly transactions rack up. So this is what it looks like from a cumulative transactions perspective. Which is like you kind of start off like really like, this initial funding and then immediately it just kind of like rips up. And so the first question people have had is like, well, how does the node even support this sort of throughput? Because like this is, potentially a considerable amount of data. And to that, you are correct. So the amount of data that this thing processes per second, I'm floating through a bunch of images here. I should have just kept the dashboard up because then I could really quickly do this. So it finalizes about 20 megabytes of data per second of transactions. Now, this is not the limit or anything like that. It's just this is what this test surfaced. And so then keeps consistent at like 20 megabytes per second of, not megabits, megabytes per second of data finalization. And so if you were to just persist this data to disk, you'd very quickly run up quite a bill. And so what was important to us, and based on what we've learned with like running all these sorts of subnets, is having a virtual machine that really looks after itself is a very important mechanism. And so the nodes in the HyperSDK are not meant to be archival nodes. They are purely meant to perform consensus and finalize data and then provide an interface to get that data off. That's it. And so I then kind of graphed or charted like what that looks like. So from a chain data perspective, it gets up to about 22 gigabytes of data on disk, and then just keeps track of its size and gets rid of old stuff. So primarily old, disk or like disk blocks and disk chunks. So that's also configurable. So like based on how much history you want the node to keep, you can do that. And then it will just get rid of stuff that is too old and then try to maintain that, basically that stable size. So what this ends up looking like is you can have a node. I think in this case, I did 32 vCPUs, 64 gigabytes of RAM, and it's a 100 gigabyte disk, and it can process 100,000 TPS sustained. And so then if you look at maybe some other cool stuff. So like I said, this is all parallelized already. So the example case we talked about was, or the one I was focused on was micropayments, which is basically just transfers. And so then I use a ZIF distribution to determine like which accounts are active at any particular time. And so if you do that, you have about 80% parallelism of transactions or so. So transactions, basically the execution engine is effective in this workload, I'll say, and can very quickly process everything. And so then people are like, well, is this workload maxing out the virtual machine? And my answer to that is no. So for example, the CPU utilization, which is a good indicator of like how much stress the system is under, sits at about 35% or so. So I guess you could probably like even further under provision the virtual machine if you wanted to like run it kind of closer. I prefer to like have a workload like this run at like 30 to 45% just to give some headroom in the case of some sort of issue. You can see some of these like kind of spikes on the chart for any number of reasons, but it's definitely not maxed out. Our view is that we're trying to get to like a certain workload goal, and then at that point I think you can get pretty carried away excuse me, when you go past that. And so let me see here. Here's an image of the state changes per second. So you can see it's about 95,000 or so. And so the mechanisms to make this all work are interesting and a combination of a lot of different things. I would say like one of the bigger tweaks. So, I'll first actually talk about like what's going on here. So first off, this is all only possible because of Vryx. So with the same test on the HyperSDK pre-Vryx, it won't come anywhere close to this. And the reason for that is which I've talked about at length in the Vryx calls and in writing, is that the loop of block production to dissemination to all of that, like it simply just like really fills up the block execution loop, and like there are just restrictions, right? Like if I have a block and that block contains the transactions, and you want to verify everything in that block, like there's just a natural distribution or like dissemination rate at which you can go to get all these transactions throughout the network. And if you're trying to distribute that around the world and execute that block while you're trying to verify it, like the network will very quickly become unstable. And so the Vryx idea, right, is to distribute the transactions prior to their inclusion, and then just have the blocks themselves really just include reference to the transactions that are going to be included, or chunks of them that have already been reliably disseminated, and then execute the blocks asynchronously. And so in the step where we actually distribute the chunks and get like a certain signature weight, that takes about 250 milliseconds on average to get all the chunk signatures needed to actually include a block or include a chunk in a block or a signature in a block. Now, for the reader at home, like you'll see these spikes again. This is related to the disk IOPS thing I was talking about. But generally speaking, you see these like kind of different tiers of lines. And that's really just a reflection of like where those validators are in relation to everybody else when they're like trying to collect these signatures. But the gist of it is, in standard networking conditions on high performance hardware, you can get signatures collected pretty quickly for a certificate. And in a standard user application, this is the point at which you would probably be able to provide like an initial feedback to the user that like their signature or their transaction is very likely to be included at some point. I think throughput test here. Obviously, it wasn't adversarial, but like 100% of transactions that were included in chunks were eventually included on chain. And that average time at which they were included was about end to end from issuer to getting issuer confirmation was about 3 seconds. So you would know very quickly whether or not like you probably weren't going to get included. But in this case, like, you know, it wasn't operating at a level where things weren't getting included. And so this is the step that it basically goes before block distribution. And so you do the signatures, you collect those. That ended up being pretty quick, no matter where you were in the world. And then when you get those back, you can put them in blocks, and those blocks, and then you come to consensus over them. Now, in the traditional like HyperSDK, like the amount of time spent in consensus was roughly, I think it was something like it almost went up to like 1 second per second of time spent in consensus, either like verifying blocks, like processing messages or whatever. And when you get above 1 second per second of time spent in consensus, you start to have issues because we only have 1 second per second. And so with the new HyperSDK, I think it never really surpasses what I think is about 150 milliseconds per second. So there's a significantly more headroom in its ability to actually like handle consensus operations. And the reason for that is like most of the time consuming things that would typically be done in like consensus message handling are done now asynchronously or really outside of that. Let's see. Yeah, maybe I'll pause here. I don't know if anyone has any questions or stuff. Try to be thorough with the testing that we've done and really tried to strive to make things as reproducible as possible at every step of the way, because you can't make performance claims, I think, without really giving people the tools to replicate those things. So you have all the code and you have all the scripts and you have everything that will get the exact same results that I've gotten here, minus the spikes.
I think there was a question asking how much does running this test cost?
Yeah, so it's I think right now it's a C7G 8x large is the instance being used. I think that's the same price as a C5 4x large. So I think it's per node. Let me look it up. I don't know if you guys have been at this site, Amazon EC2 instance comparison. Super sick. All right. So C7G 8x large is on a reserved price, 76 cents per hour. So if you were to run all 50 validators, I think that test ran for 18 hours. So about $500 or so to run the full test, minus the disk costs, so it's probably going to be about $700 or so. Now, again, the point with this test is to demonstrate. Actually, I'm really curious before I do this what the C5 4x large price is. So it's a little bit cheaper. So it's closer to, yeah. So like a C5 4x large for a single node is like it's maybe 20% or so more than that. And like I said, you have a lot of headroom, so you could try to run the same test with smaller machines. But yeah, the idea here is like if it can, a big question or like conversation Steve and I have sometimes gone back and forth on is like, you end up having to make certain trade-off decisions as you try to go to different levels of capacity. It's just the way it works. Like things that work at 10 TPS don't work at 100 TPS, definitely don't work at 1,000 TPS, and definitely don't work at 100,000 TPS. And so that's not to say that like some of the things that you optimize for the 100,000 threshold don't make things much more efficient at like the 100 TPS or like even the 1,000 TPS level, but you end up sometimes losing some capability through that process. And so one thing that we've talked about is really like what we want from the state management layer. So traditionally, like there are three things that people want from a state management layer. They are like, I can prove arbitrary key values at some state. I can verify that everyone that is operating on the state has applied the same state transitions. And I can verifiably sync that state from other people in the network. If you want to maintain all three of those invariants, typically people use a Merkle tree and then they like try to optimize around that Merkle tree. So, you know, we've definitely gone down that path in two ways with MerkleDB and with like Firewood. The design space opens considerably if you relax the first constraint, which is that you don't need to prove any particular key value in state. You can make things a lot more efficient, but at the same time, like I said, you get this, you just make a trade-off in functionality. So this is a perfect example of like what you'd want to do as you move up the throughput stack. So I think the HyperSDK is really trying to be great for that like 10,000 to 100,000 or more throughput category. And if you're trying to use it for something less than that, I think that the trade-offs it makes from a capability perspective may not be like just like optimal for you. The next question, which I definitely wanted to touch on, is did you test how the throughput changes? Yeah, so I ran it at 25 nodes and then at 50 nodes, and there was no difference in the performance of things. Now, the reason for that is that Vryx is symmetric, I think. So the way that that works is like, because of the way distribution of everything happens within Vryx for transactions, it's always symmetric. So like you distribute your information and then people distribute back to you. And then because addresses are partitioned across like all validators that can actually include you, you can't really like force like one partition to get too much hotter than another partition. And so it ends up being this really nice property where like the more nodes you add, actually like the less work any particular node has to do, which is kind of even better. So the only difference is just on the consensus payload side, where you end up having to like distribute the block to more participants and potentially like pull more people in consensus. But as we've seen with Avalanche consensus, like on mainnet, it has like what, 1,800 validators. So the bottleneck at that point is not actually the distribution of data. It goes back into like what we're doing on the consensus side. So I haven't tested like 100 or 200 or 1,000 participants, but I would expect that with the way that it's currently performing, that you could continue to increase that number. You just have to kind of like draw the line at some point to start to share the data. This is the first DevNet, remind you.
I'd be really interested on like the chunk like signature aggregation step as like the number of nodes grows up, because like the number of like attestations that you need for a chunk to be valid is going to grow up as well.
Yeah, I think the benefit
specifically
with that is that is already like a pretty parallelizable thing. So there's like really great ways you can already do that. And then I actually already cache the public keys from the aggregate signatures. So there's no like regeneration of that either. So yeah, I think there are just nice properties that will let it continue to handle that growth pretty nicely. The big question just really is really all the mechanisms around like how many chunks are actually managed. Because like if you continue to allow each participant to produce some number of chunks, like the number of transactions won't go up, but the number of chunks will go up 5x, 10x, or whatever as you increase the number of participants. I haven't seen that cause an issue yet, but I would imagine that that could be potentially some cause of an issue. Yeah. So long story short, this is the first DevNet. There are definitely things that won't work right. Like you will definitely find bugs. I can't wait to learn about the bugs you find. But the initial progress and results have been good. All right, so I have a C question here from Josh, which is, there are just regular transactions that are being put. Is there any expectation that if they're AWM heavy, it would cause a very different profile? So these are simple transfers right now, mostly because we don't have other things fully fleshed out to test on like more complex load patterns. You would expect that that would increase definitely the latency for like any particular transaction to be executed. Now, if you had infinite cores, this wouldn't be a problem, because assuming that you had the same rate of like parallelism that I've displayed before, if every transaction takes 5 milliseconds and you just had like, infinite cores, you could just process everything in 5 milliseconds, right? Minus like modulo, whatever isn't parallelizable. That's not obviously realistic. And so like the amount of time that each transaction takes definitely has a bearing on like what your maximum throughput is, assuming you are trying to like process a block within a second, which is what I require in this example. And so in that world, you would expect the throughput to go down. I would expect. If you're talking about the AWM case, I wouldn't, because I think, with AWM, it's all, again, like you could parallelize all those verifications. So as long as Avalanche Go allows you to like verify them in parallel, which all I'm doing is requesting basically the signers for some subnet, that operation is pretty quick, and you can do that asynchronously. So I don't think that would cause a huge drawdown if it was optimized. I'm more concerned at this point with like what are the theoretical edges kind of that would hurt us, not the like in the current form, which is definitely unoptimized. And so in that world, I do believe that it wouldn't be, you could find a way to make it efficient, basically, if it was like an AWM heavy workload. I guess if you had like 10 HyperSDKs all like sending 10,000 more messages to each other all the time, I think that'd be interesting. Be an interesting test to see how that performs at some point. My hope is that some of the frameworks that are shared here can be utilized for your guys' testing too. Like they're all available and open in the repo, so you can basically just replace. So in the script, you just kind of pull this commit, which determines like what code it's running. So you could replace this commit with literally anything, and as long as it was working with the configurations, you can test your thing in the exact same setup. So if you just like basically forked my branch and then just added random shit, you could test this all. Another question I saw was like, what about joining the network? So the joining the network is a function of the state size. So with 10 million accounts, that's roughly 500 megabytes or so. So depends on your bandwidth to be able to pull that, but I would expect pretty quick. I think the point there being is like, I don't view full sync as a viable option at this throughput. Like you just can't do that with this much data, and like what other nodes would have to store. So like people can offboard that data to like some other data infrastructure that they could then sync, and it's all verifiable, right? Because it's all hashed. But the nodes, I don't think will perform that. The nodes will just help you get to the current state. And with some database designs, you don't even need to have that be on the node. You can also offload that to some other mechanism if you wanted to. But it's really just a function of how quickly can you sync 500 megabytes in this case. But obviously, if your state's much larger, it's just a question of like how quickly can you synchronize that. Now, if you had a Merkle tree there, you'll be doing like range proofs and stuff like that, but those are pretty quick still. If you have another mechanism, which is more like checksum based, like it may be easier to parallelize that load and just fetch it from like a CDN if you wanted to, or just the nodes themselves. I see one question from Patrick. If we are currently building custom actions on top of the HyperSDK, will it be easy to transition all of our implementations on top of Vryx? Yeah, like I said, I didn't change anything really in my handling of stuff at the actions. The whole point is this is supposed to be behind the scenes. I think the only thing of note is that with the chunks, fees become a little bit more dumb, I'll say, to prevent like people from gaming the system. And so you just don't have fee refunds anymore during the execution. And so the reason for that is if you have refunds, then people can claim to use like many more units than they would, pushing the chunk that's going to be distributed to like its max size. And then in practice, not actually use them and then not actually pay all the fees. And then you could like trivially fill a chunk with like some large transaction that ends up doing nothing and then dramatically drive down the revenue of any chunk builder. So you could either have refunds and then limit how many resources any single transaction could use, or just get rid of refunds. And I felt that the best option was to remove refund support. And so you basically just could charge the fee that you claim that you're going to use at that time. So that's probably the biggest user interface or like developer interface change that was required to make this safe. This to me goes back to that question of like, what are the trade-offs you're making to hit the throughput you're trying to target? So if you're trying to hit, something where you don't need to like pre-distribute transactions and occupy like your limited replication bandwidth, then you can get away with generating executing the transactions prior to distribution. But if you can't get away with that, then you have to make trade-offs to make it safe, either limiting like the max usage any transaction can have, or just charging whatever they say that they're going to do. So I think that's one thing that could use potentially more research, but I couldn't think of a way to get around that issue that wasn't like trivially gameable. So in essence, that works really well for like payment architecture, like kind of like marketplace architecture. It doesn't work as well for like massive arbitrage transactions or something. Unless you're willing to just eat the cost of like some potential like massive CPU requirement that doesn't get filled. And that may be okay if the fees are low enough, but that's how to think about that potential trade-off.
Doesn't sound impossible to still have refunds, right? Like, because we already are filtering out like invalid TXs for like an invalid chunk producer, right? So like, if you just like allocate a fixed amount of bandwidth in the chunk, and then as you execute, once you hit your cap, then like the remaining get filtered.
It gets weird because that's also happening concurrently. So you have to be very careful about exactly when you stop and kind of stop applying state. You'd almost have to have like I think like an end op on like the concurrent execution to make sure that like you basically commit those things to the pending state in the same order or just drop them. So you could do it. So to back up, from a theoretical perspective, I agree with you. Like you could allow people to basically just say, here's your bandwidth. If you're under your bandwidth, but you've maxed out other resources and we're giving you refunds, yeah, just keep filling it up until you hit your limit. And you don't have to, but if you want to, you can. And then as soon as like during execution, we hit that limit, we just stop. And because of the filtering we already have for chunks, like it doesn't actually end up like weighing the system down at all. Really just it interacts with like the pending bandwidth of like these processing chunks. So you want to write part of that? Yeah.
Sweet. Do we have any more questions or maybe just like general questions about the HyperSDK?
I have a couple, if it's all right. I was just looking at the token VM example primarily. I think it's a really good like starting point for somebody that's just trying to get like dip their toes into what it means to build with the HyperSDK. I see a few opportunities for like dev tooling to maybe reduce some of the frictions with like building out some of the kind of boilerplate around actions and like JSON RPC calls, stuff like that. I was just wondering if you guys have like thought about that at all, if that's something that you'd like to see other people getting a bit more involved in, or what your thoughts are on that.
There will be a massive opportunity, just like with the Cosmos SDK, to produce like a bunch of HyperSDK generic tooling, in my opinion. I think this will become even more appealing because the HyperSDK currently offers like these custom RPCs, as it sounds like you've seen. That will be removed with the Vryx integration, and there will be an expectation that all of that stuff, or like any sort of custom RPCs you want to support, will be an externally run mechanism. You could run that in the same box if you wanted to, but it's not going to be run within the Hyper-VM binary. And so there will be room for this like generic kind of architecture that sits next to the HyperSDK that ingests like the state diffs, the transactions, and then offers like some sort of RPC experience. So we'll try to offer like a bare bones version of that, but you could imagine quite a long tail of interesting ways to take that, I guess. Yeah.
Got it.
The actions themselves, like I think they require you to like manually pack state and manually pack that like the actions actually in the transaction. Some people don't want to do that. And so like having like some sort of like wrapper you can like invoke or like something like that that is like standardly like parsed by some sort of other systems may also be like a nice thing. So in a nutshell, yeah, I think there's still some changes underneath that will be made before it makes sense to like commit to like a perfect design, but like there will definitely be room for like general wallets, general explorers, general kind of like RPC handlers, stuff like that.
For sure. Thank you. I just had one more. I was wondering if you guys could share any insights on timelines in terms of like audits. I know it's like obviously an alpha phase right now, but just roughly like when you're going to be moving towards maybe more of a beta phase with the whole project.
Yeah, so the this is on that roadmap. I think we shared it a little while ago, but the idea was to get this POC complete. Took a little bit more elbow grease than I expected to get it to the throughput we wanted. I think we got it to the throughput we wanted with like 10,000 accounts a month ago, a month and a half ago. And then, you know, when I was talking about it with some folks, they were like, 10,000 accounts. I mean, come on, like that's not a real like real test. And so I was like, all right, fair enough. So I put it to 10 million, and then rightly so, things didn't work quite the same. So had to rethink some other pieces to make it fast enough. Now that we have that, the point of doing this like viability test was to be as thorough as we could to try and speed up a production implementation and try to answer the difficult questions now. My hope is that still by the end of Q2, we have like some sort of basic DevNet, that like a long running kind of test net, maybe just on the Morpheus VM that's publicly accessible. And then after that point, we could potentially start to kick off some sort of auditing process. My hope would be that we'd be production ready maybe by the end of Q3 is our aggressive estimate.
Yeah, we've kind of described it into like we're in this like discovery hardening phase, and then we're going to try to get to like an integration ready phase where you could start doing like this JSON RPC or Explorer or wallet support. And then as we do the integration ready, like really be thorough and then get it to this production ready state.
Yeah, I mean, I think the part to emphasize there is like we're trying to minimize the complexity of the core of the HyperSDK so that the scope is better constrained. So people have also asked me like, hey, like all these Vryx changes, they probably made it like way more complicated, right? And the answer to that is actually no. It made it simpler than the way it was before. Like in the old way, you had to do a bunch of like crazy optimistic stuff to try and make it hit that throughput. And in the failure pattern case, like complicated. In this world, it's actually pretty straightforward because you just rely on these like the chunk distribution. And if the chunk distribution makes sense, you get this little signature, you put in a block. If the blocks get verified, you just execute. So there's no crazy like gossip stuff you have to do. There's no crazy like really quick dissemination the leader has to do or something like that. So it's in this very interesting category of, in my opinion, being more robust, faster, and simpler. So sign me up for that. I think it's just the trade-offs you end up having to make with some of these like fee dynamics and things that are potentially the rub. So don't let anyone tell you there's no trade-offs in something. So there are trade-offs.
Thanks, Evan. Any more questions? I know we're almost at time, so we could always wrap up a little early.
Cool. I want to just emphasize, don't share any of this yet. You're part of the early release crew, I guess. I'm working on typing up all of this, what I've kind of shared with you, the learnings, and we hope to post this in the next day or so. It will definitely be posted prior to this video being posted, so don't worry about that. Yeah.
Well, thank you all for the questions. Hope you enjoyed the preview. We'll see you guys at the next one.
Thanks,
Thanks, everybody.
Bye-bye.
Thank you, guys.
Thanks, guys.